glomerulus and Bowman's capsule. Another process was reabsorption. This occurs along the entire length of the nephron except at Bowman's capsule, and it involves the second capillary bed, the peritubular capillaries. And this is in the opposite direction from filtration. It's reclaiming chemicals back into our body. It's kind of like absorption, but then there's a little bit more to it. We also have secretion. It occurs in the same place that reabsorption does. It goes in the same direction as filtration. This is our second chance to get rid of chemicals. We go from the peritubular capillaries into the tubule lumen. Remember, the tubule lumen is considered outside our body. And then excretion. Once we're done forming the urine, fluid leaves the collecting duct. That's the process of excretion, and this is just urine leaving the kidney. So at this point, we're not going to modify that filtrate anymore. We consider it urine. It's on its way to the urinary bladder. And then finally, micturition is voiding urine from the bladder, right? Emptying the bladder. This is the slide we saw before, right? Okay. In this is a summary of those different processes, just to kind of get it straight in your head, the direction these processes are going. Filtration occurring between the glomerulus and the Bowman's capsule. This is fluid leaving the glomerulus going into the lumen of the tubule. Reabsorption goes in the opposite direction back into our body. This is involving the peritubular capillaries and the rest of the nephron. Secretion's in the same place, but it's getting rid of chemicals, going from the peritubular capillaries into the tubule lumen. And excretion is now urine leaving the nephron, going through the renal pelvis down towards the urinary bladder. The flow rate through the nephron. This is just another way to sort of put these processes together and kind of get an idea of how they relate to each other. The volume of urine that gets excreted from a nephron will be equal to the original volume that got filtered, so all that fluid we stuck into the tubule at the beginning, minus the volume reabsorbed, because whatever we reabsorb, we're not excreting, we're holding on to it, we're taking it back into our body, plus the volume that we secreted. Right, to secrete is going to be getting rid of it, putting it in the tubule lumen. So filtering and secreting is a process to get rid of chemicals. Reabsorption is to take it back and to hold on to it. Alright, everybody got that? This figure shows the previous slide, just with a little picture associated with it. It kind of combines the last two pictures. Right, so the amount filtered, where we originally dump all that fluid into the tubule lumen, subtract the reabsorption, what we hold on to, add what we secrete down the line, and what you get at the end is the amount that you actually excrete. Okay? Alright, so what volumes are we really talking about? This table here gives us a rough idea. So we've got different areas along the nephron in the first column. The second column shows us the rate that fluid flows through all of our nephrons together. So this is for both kidneys combined, and this is over a period of the whole day. So the amount that we actually filter at all of our Bowman's capsules is about 180 liters per day. That's a huge volume. Right? Remember where all this fluid comes from. This is part of our blood. How much blood do we have in our bodies? Kind of sort of 5 liters. Well, we're filtering 180 liters every day. Clearly that alone is not sustainable. Right? We'd run out of blood volume within the first hour. Right? Pretty soon, early in the day, we'd be out of fluid. So we can't just leave all that fluid in the tubule lumen and excrete it all. We've got to take back most all of it. By the time we get to the end of the proximal convoluted tubule, so that's that first section after the Bowman's capsule and the tubule, we're down to only 54 liters per day passing through that section. So we've already reabsorbed, almost 130 liters every day by the time you've gone through the proximal convoluted tubule. So we reclaim most all of that water right off in the beginning. When you get through the loop of Henle, we're down to only 18 liters per day. 1/10 of what we've originally filtered we've already, whereas is left in the tubule, so 9/10 we've already reabsorbed almost all of it. And by the time you get to the end of the collecting duct, when you actually go through excretion, you're losing only 1.5 liters per day. That's about how much urine is produced a day. Yeah, it varies a tremendous amount. Are you drinking a ton of water? Are you really dehydrate? All those things go into it. But just to give you some rough ideas, you're excreting 1.5 liters per day, where you originally filtered 180 liters. That's a big difference. So there is a lot going on during that time that fluid flows through the nephron. Right? You filter a lot of it, but you reclaim or reabsorb almost all of it. Okay, questions? Yes?
Is the majority, like what's the majority of that fluid? Is it just like blood, like H2O, plasma, like what's?
What gets filtered?
Yeah.
So it's not blood. It's not whole blood. If it was,
Yeah.
then you'd be peeing blood all the time. That would be a problem.
Scary, yeah.
Yeah, so that's not really what you want. So, we'll talk in a little more detail about that very soon, but it's essentially blood plasma,
Yeah.
except for most of the proteins.
Okay.
The cells stay behind, stay in the blood.
Okay.
Yeah, question?
Do we have to know the specific volumes, averages per location, or just the kind of general?
You think that's a good idea to remember those?
No.
No, I'm not going to ask you to remember those numbers. But the reason I'm showing you the table is I just want to sort of emphasize the amount of reabsorption that occurs and the tremendous amount of volume that gets sort of adjusted or filtered as it goes through the nephrons. Right, so yeah, I'm not going to ask you those actual values. Okay, anything else? Okay. All right, let's go and look at each of those processes in a little more detail now. Filtration. So remember, filtration, this is half of bulk flow. This is the half where material leaves a blood vessel, and in this case, goes into the tubule lumen. And filtration at a nephron only occurs at the renal corpuscle. The renal corpuscle. Remember, the renal corpuscle is made up of the glomerulus and Bowman's capsule. Those two together are the renal corpuscle.
Urinary and what?
Bowman's capsule. You may also see it as the glomerular capsule, same thing. All right, what gets filtered? We just talked about this. It's water and dissolved solutes, all the stuff that's in the water. Blood plasma. Blood plasma, except for most of the proteins, stay in the blood. So it's just like in any other capillary bed. All right, let's take a closer look at the path of filtration. And if you were to follow, say, a water molecule, what is it actually going through to get through that renal corpuscle? Well, it first has to pass the glomerular endothelium. So the glomerulus, remember, it's a ball of capillaries. And a capillary is made up of a single layer of really flat cells. That's what this glomerular endothelium is. So it has to go across those thin cells. There's a basement membrane. This is an acellular structure. So the glomerulus is made of epithelial tissue. All epithelial tissues have a basement membrane. This is what anchors the tissue to something else. So it goes across the basement membrane, which is not very thick. And then it has to go through Bowman's capsule epithelium. So a thin layer of flat, a single layer of flat cells that makes up the lining of Bowman's capsule. So it's two layers of thin cells held together by a basement membrane. That's what the chemicals have to go across for filtration. Okay. Let's look at a drawing that shows this. So at the top here we have the glomerulus in red that's surrounded by Bowman's capsule in yellow. So Bowman's capsule, remember, it's surrounding this ball of capillaries. So if my right hand is the glomerulus, that's the ball of capillaries, you've got this capsule around it. But there's a space in there, a lumen to the tubule inside there that's continuous with the proximal convoluted tubule. So this capsule really needs two layers to it. there's an outer layer, and then there's also the inner layer that comes in contact with each of those capillaries making up the glomerulus. And that inner layer is what these little yellow things with the little branches that come off represent, and that's continuous with this outer layer. You go ahead and look at that up close, and we can see an individual capillary in here surrounded by this cell here, that podocyte. That's a cell that makes up the lining of the glomerular capsule, or Bowman's capsule. That's what we call it. So this cell makes up that lining, the inside part of the Bowman's capsule. Out here, these cells make up the outer portion. Between the two, that's the space of the lumen inside Bowman's capsule. Everybody picture this? Anybody not picture this? Anyone? Yes?
It's the same kind of cells?
Inside versus outside? No, the ones on the inside, they have these little sort of legs or feet to them. That's what the podopart refers to. And the outside, those are just squamous cells. The spot cells are all locked together. Yeah?
Sorry, what was the podocyte again?
Podocyte, these are the cells that make up that inner lining to Bowman's capsule. And that's the part that comes in contact with the glomerulus, those capillaries. Is there another hand that shot up? No. Everybody feel good about the setup here? So, I find it interesting. So, this class, the previous class I taught today, and the one I taught yesterday morning, we're all equally energized and enthused. Or not. You guys are already on Thanksgiving break?
What's the miasma in there?
Okay, that's one way to word it. All right. So here's another drawing, so it shows all this relationship a little bit different way. The top, that represents the lumen in the glomerulus, the capillary. The bottom represents the lumen of the tubule made up of Bowman's capsule. And these big chunks here represent the individual cells that make up these structures. And the blue here, that's the basement membrane. Okay. So these cells are going to form the capillaries making up the glomerulus. These cells form the lining, the inner layer to Bowman's capsule. There's another layer of cells outside here. And those together form that lumen there. So with filtration, chemicals are going to go from the lumen of the glomerulus past the glomerular cells, past Bowman capsule cells, into the lumen of the tubule, and that would be filtration. Okay. All right, in this figure, again, we've got our glomerulus here. This inner yellow portion, that would be made up of those podocytes. They've sort of exaggerated the space between the two. But the cells that make up this inner portion will be wrapped around that glomerulus. So the cells that went across the wall of the capillary, across the inner layer of Bowman's capsule, would be in this space here, in that lumen. Okay? And the numbers here, it shows 100, I don't want to go back to, shows the rate that blood flows into the glomerulus, the rate the filtration occurs, and about 20% of your resting cardiac output's going to all your nephrons. About 20% of that is actually what gets filtered. Right? And so that's what they're trying to show with these numbers. So 20% of the blood that flows into the glomerulus by volume gets filtered into the tubule lumen. Okay? All right, let's look at what's driving this filtration, the forces involved. This part's kind of a review, because we've already talked about bulk flow. So you know what contributes to filtration. So let's review. All right, there's a hydrostatic pressure involved due to the pressure in the capillaries. These are the glomerular capillaries. That's the blood pressure in there. This blood pressure is around 60 millimeters of mercury. It's higher than typical capillary. So that pressure in the glomeruli is fairly high. Another pressure involved is the osmotic pressure in the capillary. So this is the same osmotic pressure that we saw in a typical capillary bed. This is due to those proteins that stay behind in the blood vessels when most of that plasma filters out. You take out some of that plasma, leaving the proteins behind, that makes that fluid in the blood vessels more concentrated, a higher osmotic concentration, and that's where this osmotic pressure comes from. And this pressure is about minus 29 millimeters of mercury. Remember, minus pressures in this case represent absorptive forces, where positive pressures represent filtration forces. Another pressure involved, the hydrostatic pressure in Bowman's capsule. When we talked about bulk flow before, we said this pressure is essentially at zero. We don't really build pressure up in the surrounding tissues. But in this case, Bowman's capsule is partially enclosed. So when we shove fluid into Bowman's capsule, that actually does develop a hydrostatic pressure in there. And this is at about minus 15 millimeters of mercury. To figure out the net pressure, you add up all three pressures, right? What does that come out to? 44, minus 44 millimeters of mercury pressure for this one. So, what's that, 16 millimeters of mercury positive pressure? This slide's going to do the math for us, I think. All right, so here in the blue arrows, that represents all these pressures. So we've got the hydrostatic pressure due to the glomerular capillaries, the osmotic pressure due to the proteins that stay behind in the glomerulus, hydrostatic pressure due to the fluid in Bowman's capsule. So we've got a positive 60 millimeters of mercury for that blood pressure, minus 15 millimeters of mercury for the fluid pressure in the Bowman's capsule, and minus 29 millimeters of mercury for osmotic pressure. Add all those together. See here, I think it's super confusing how to use pluses and minuses, but it comes out to a positive 16 millimeters of mercury as a filtration pressure. Yeah.
Why isn't there an osmotic pressure for the Bowman's capsule?
So the proteins that are in the blood do not get filtered. They stay behind the blood vessels, and that's based on an osmotic gradient. And so that minus 29 millimeters of mercury pressure accounts for all the osmotic particles in Bowman's capsule and all the osmotic particles in the glomerulus. And that comes out to, it already sort of figured out the difference between the two. A definition, right? So osmotic pressure is based on the osmotic gradient. You gotta know what's in both sides.
Okay.
Anything else? All right. So now we know why we only get filtration in the renal corpuscle. We don't get absorption. And it's because of these pressures. Right? We've got a relatively high blood pressure coming in that stays high through the entire glomerulus, higher than the absorptive pressures. Questions about that? Yes?
That it's always going to be positive, so it's all never absorbing.
When you're healthy, yes. There's weird things that can happen, but yeah, it's always going to be a positive filtration pressure. Okay, anything else?
Negative filtration pressure doesn't mean that you have kidney failure.
Well, if it was a negative pressure, it wouldn't be a filtration pressure, it would be absorption pressure. Would it be kidney failure? So I guess you would get that if, for whatever reason, you weren't getting any blood flow to your kidneys, and your kidneys would shut down. That'd be bad news. Or for some reason there was some huge osmotic pressure inside, the concentration inside the tubule lumen, wherever that would happen. So yeah, it would, things would be going really bad with your kidneys if that happened.
Does the pressure change when you only have one kidney? Like, would it be higher pressure?
Right.
Or like,
I don't know. My first thought is not necessarily, but I don't know. Anything else?
How can we measure that pressure? Like, how did they come up with these numbers?
How did they come up with these numbers? I don't know, I wasn't there. With the
Little blood pressure cuff?
yeah, stick it right around the tubule. My guess, yeah, first off, I don't know. You guys are asking all these questions, I don't know. You guys are really good at that. My guess is that they estimated what the individual pressures are based on the total flows in and out. And sampling those fluids to get an idea of what the osmotic concentrations are. That's my guess. I don't know.
So it's not super accurate.
Well, I don't know, because I don't know what the methods were. Not sure. I mean, these particular numbers are not, right? So they're going to vary from individual to individual throughout the day and the year and so on. But they're accurate enough to explain the trends. Okay. Any other questions? I don't know. All right. What do I want to show about this figure? Here's a renal corpuscle. Filtration is going on. All right. Let's look at glomerular filtration rate. So the rate that fluid is filtered from the glomerulus into Bowman's capsule. You can abbreviate that with GFR, glomerular filtration rate. All right, if we were to look at the rate over a range of pressures, right, so in this graph we have mean arterial pressure on the horizontal axis, we've got glomerular filtration rate on the vertical axis. First off, what is mean arterial pressure? When you measure your blood pressure, you get two numbers, right? A systolic pressure and a diastolic pressure. That's kind of clunky to deal with because you've got two different numbers. It'd be really handy just to have one number, and that's where this mean arterial pressure comes in. It takes an average, and it's not just add those two pressures up and divide by 2. It's a little more than that because your blood pressure spends a little bit more time towards the diastolic end than it does the systolic end. So it's not quite as easy as adding the two numbers together and divide by 2. But this is that mean arterial pressure. This is an estimate of what the average pressure is in your arteries. And as that pressure, the mean arterial pressure increases, the glomerular filtration rate increases. Kind of. There's this range in the middle here, though, where GFR is fairly stable and flat. Does not change with a change in blood pressure. And this happens to coincide with a typical range of blood pressures. Right? So your blood pressure generally is in this range. And so in this range, your GFR doesn't really change. It stays pretty constant. Right? Your glomerular filtration rate does not fluctuate under normal situations. If you get out to the ends, then yeah, it does. If your blood pressure drops really low, glomerular filtration rate drops off a lot. The last thing you want to do with really low blood pressure is filter more of your blood out. If your blood pressure shoots up really high, then your GFR is going to start going up. Right? And you're going to start producing a lot more urine, getting rid of a lot more fluid. All right, let's see what goes into this. So your GFR is in part based on your filtration coefficient. How easy is it for filtration to occur? This will be based in part on the surface area for filtration. The surface area is huge. Right? So this is the surface area of all the capillaries that make up all of your glomeruli. That's an enormous surface area. Each little glomerulus has a huge surface area, and you've got about 1 million of these in each one of your kidneys. It's a huge surface area. It's also based on corpuscle permeability. Well, your corpuscles are really permeable. They're super leaky. We saw that in the drawing of those podocytes. There are gaps between the cells. And that's really leaky, allows for a lot of filtration to occur. It's also based on filtration pressure. Right, we just talked about all those pressures involved in filtration with the renal corpuscle. And so those pressures can influence your GFR. You start playing with those pressures, raising or lowering them, it's going to change your filtration rate. So let's take a closer look at these pressures. All right, so filtration pressure. If you increase resistance to flow through a vessel or tube, you're going to decrease blood flow downstream of that resistance. So you've got this blood vessel here, blood's flowing through, increased resistance, maybe make it skinnier, constrict it. Now, not as much blood's going to go through, so you're going to get less blood flow downstream of that constriction, for instance. So, if you increase afferent arterial constriction, what does that mean? So remember, you've got two different arterioles for each glomerulus. The afferent arteriole carries blood into the glomerulus. The efferent arteriole drains blood out of the glomerulus. So if we increase constriction on the afferent arteriole, make the one that leads to the glomerulus skinnier, adds more resistance to flow, less blood's going to make it into the glomeruli, which drops the blood pressure in there, and that's going to decrease GFR. Let's look at a diagram that shows this. So in yellow we've got our tubule, the little V represents Bowman's capsule, and the V in the pink or red, that represents your glomerulus. If you constrict the afferent arteriole, there's more resistance to flow, then less blood flows into the glomerulus, you have a reduced GFR. You dilate that afferent arteriole, more blood comes in, you increase GFR. So that's one way to adjust the blood pressure in there and to adjust GFR. Which leads us to a discussion of GFR autoregulation. So your kidneys regulate this GFR all on their own. They don't need an influence from your nervous system, for instance, or endocrine system to control GFR and to keep it really stable across that range of blood pressures. Let's look at the mechanisms involved. So one of them is a myogenic response. What does myogenic mean? Well, myo means what? Muscle. Genic, the origin of, or the genesis of. So myogenic means it comes from muscles. And this is based off the idea that a stretched muscle will contract. So smooth muscle, if you've got a sheet of smooth muscle and you go ahead and stretch it, that stimulates the smooth muscle to contract, resist that stretching. Let's apply this to those arterioles. If for some reason the flow to your glomeruli starts to go up, you increase flow. That's going to cause your afferent arterioles to stretch, which stimulates them to constrict down. The smooth muscle is going to contract, and so you're going to have increased vasoconstriction. Those afferent arterioles constrict down, which increases the resistance to flow, which decreases flow. So you have a surge of blood pressure in the body for some reason. That afferent arteriole swells up. Your immediate response is to resist that, to go back to where it was, to keep that extra flow from occurring. This is a way to keep it in check, to keep that GFR from rising. Does this make sense to everybody? What does this flow chart show us? So if you have an increase in mean arterial pressure, your blood pressure in your body goes up. Your afferent arterial pressure goes up. That causes the smooth muscle in the walls of that arteriole to stretch, stimulating them to constrict. Right? So those vessels get smaller again, go back to their original size, increases resistance to flow, decreases the pressure in your glomeruli, which would decrease GFR, bring it back down. Right? So before this response happened, right, you've got this increased pressure in your afferent arteriole, you get a rise in GFR, but that myogenic response provides that negative feedback, shutting it off, keeping you from having that extra flow. Make sense? Oh my gosh. All right. So going back to this figure, so within this range, right, if your blood pressure shoots up, then your afferent arterioles are going to constrict back down to keep that extra flow from occurring with the glomeruli and keep your GFR nice and stable. And again, it doesn't need your brain to figure all this out. It does it all right there at their arterioles. All right, another mechanism, tubular glomerular feedback. All right, so we'll get feedback from the tubule that will influence the glomerulus. How did that happen, right? All right, so the distal tubule can signal to those arterioles. Remember the relationship between the distal convoluted tubule and the arterioles. When that loop of Henle comes back up through the medulla to the cortex, and it transitions into the distal convoluted tubule, that distal convoluted tubule is right between the two arterioles. And that distal convoluted tubule with those arterioles together forms what structure?
Juxtamedullary apparatus.
Juxtaglomerular apparatus. So close. But much better than anyone else in this class has guessed. So thank you for contributing. Anyone else? All right. So here's the juxtaglomerular apparatus. We've got that distal convoluted tubule that's right between those two arterioles. And so we're going to get some feedback in here. All right, what happens in the distal tubule is going to then influence that afferent arteriole. Let's see how that works. All right, so if you increase flow, let's say GFR goes up, you've got more flow through the tubule. That means you're going to have an increase in flow through the distal convoluted tubule. That stimulates the cells that make up the wall of the distal convoluted tubule to release paracrines. Paracrines are chemical messengers that act on neighboring cells. Kind of like hormones, but they don't go in the blood and go somewhere else in the body. They just act on neighboring cells. In this case, the neighboring cells are going to be on the afferent arterioles. So those paracrines stimulate the arterioles to constrict, which then leads to a decrease in flow into the glomerulus and a decrease in GFR. Again, this does not require the endocrine system or the nervous system. It's all right there in the nephron. Everybody got this down? All right, so here's another flow chart. So if your blood pressure goes up, the pressure in your afferent arteriole goes up, higher pressure in your glomeruli, you increase GFR, so now you're filtering more fluid. That extra fluid goes through the tubule. The macula densa is right there at the distal convoluted tubule, so you've got more flow in the distal convoluted tubule. Those cells release paracrines that then go and signal to the afferent arteriole, the arterioles in general, to constrict, which adds resistance to flow, which is going to decrease the glomerular pressure and then leads to a drop in GFR. So two different ways to keep GFR in check with a rise in blood pressure. So those two together can help keep your GFR nice and stable over a range of blood pressures in the body. Questions about that? All right. There's even more. So there are other ways to influence GFR. So hormones and neurons can influence it as well. And these would be through vasoconstrictors and vasodilators, so you can go ahead and adjust the diameter of those arterioles. You can also change the filtration coefficient.